This is Tom Anderson with Team 8, IST 554 Network Management, Spring 2019, Penn State University. I'm going to demonstrate a DNS exfiltration and tunneling attack. So we created a VPC, a virtual private cloud, on the Amazon Web Services. We're in the Northern Virginia availability zone. In our VPC, we have two subnets, a public subnet and a private subnet. The public subnet is on the 10.0.2.0/24 IP range, and the private subnet is on the 10.0.1.0/24 IP range. Each subnet has a built-in router. The router for the private subnet, everything goes through the network interface card of our NAT firewall. In our public subnet, everything goes out through an internet gateway. We have network access control lists connected to this, so we're allowing all traffic in and out through the gateway. And then in our private subnet, we're only allowing DNS traffic out through the NAT firewall. And we're allowing all TCP traffic in from our Bastion host. If we take a look at our servers, we have 3 servers in these 2 subnets. We have our Bastion host, which is running in our public subnet. That is there in order to SSH into other systems. We have a NAT firewall, which is also in the public subnet. And then we have our target secure system, which is in the private subnet. The target secure system is the system that we are going to be tunneling in and out of. We have security groups connected to all these systems. Security groups are essentially a sort of a type of firewall. In our target secure system, we have only SSH allowed in from our Bastion host. And outbound, we only have DNS allowed out to the NAT. In our NAT security group, we only have DNS allowed out, and we'll have pinging and SSH from our Bastion host, and that's all. And then our Bastion host, we're allowing SSH in from the outside and out to the subnet. So the whole entire network here is pretty well locked down, especially our target secure system, which is back behind the NAT firewall. In addition to our Northern Virginia availability zone, we also have a system out in Frankfurt, Germany. So here in Frankfurt, Germany, we have an EC2 instance called our accomplice name server. The accomplice name server is where we're going to be tunneling out to. We're going to be able to demonstrate that not only are we going to get through all of our security on our private subnet in Virginia, but we're actually going to get out across the Atlantic Ocean to another continent. So we can start out taking a look at that accomplice name server by SSHing into it. So you can see that we're using encryption certificates instead of passwords to get in and out of our systems here. You can see by the banner here that this is our accomplice name server. We've registered the domain DNSburglar.com to associate with this. On our accomplice name server, we have a bind daemon. It's configured to run on port 54 because we're going to be running our tunneling daemon on port 53, which is the usual DNS port. And we do have a zone file here for DNSburglar.com, which we can check out. So here's our zone file for DNSburglar.com. You can see that we do have 2 name servers defined. They're both on this system. We needed 2 in order to register with the registrar. They wouldn't accept it without 2 name servers. They don't distinguish, though, that we have them both running on the same system. We also have a website, www, also running on the same system. And then we have our iodine subdomains. These are actually going to enable us to do the tunnel. And then we have a special subdomain for issuing commands to our secure system. So we can go ahead and get those started. Okay, so there's our bind a daemon running. You can see that it is actually running these zones. Then we also have running on here, like I said, our tunneling server. And you can see in our options that we have it pointing to port 54 to forward all the legitimate DNS requests. So the iodine server is going to field all the special tunneling requests, and then any real requests it's going to send on to bind. Here's our simple password. That's going to be what the client passes in to connect to it. And then this is the IP address of this server, and this is our special tunneling domain. If you're wondering why they call it iodine, part of that comes from the first 3 letters. IOD means IP over DNS. And it just so happens that iodine, the element iodine, is atomic number 53, which is the DNS port. So we can go ahead and get that started. And it is now running. So it's listening over DNS for trying to get connections to t1.dnsburglar.com. And we can just show again that those are running by looking at our processes. And you can see that they're both running as processes. Okay, so let's connect to our Bastion host. So here you can see with our banner, it's our Bastion host. There's really nothing that we're going to be doing on this system other than connecting to our other systems. And so the first one we'll connect to is our network address translation firewall. And this is running again in our public subnet. Okay, so there it is. This is our NAT firewall. Even though we already have those network access control lists set up and the security groups, I also put IP tables rules on here. So we are dropping, I'm sorry, we're not dropping by default, but we actually could do that now, couldn't we? Okay, so now by policy we are dropping. We're only accepting SSH and web, but I mean these are already turned off. The web is already turned off through the network access control list and the security groups, but we're allowing domain and SSH through. And we could actually monitor that to watch things come through. And so the only packets coming through at this point are SSH on port 22 and a few UDP on port 53. All right, so let's take a look at our target domain, our target secure system. So we'll go into our Bastion host again. And our target secure system is on our private subnet. Okay, there we are. Target secure system. So the first thing that I'd like to demonstrate with our target secure system, well, I guess first thing we can do is we can show that we can't do anything with it. So if we tried to ping out, for instance, it's not going to allow us to do that. If we wanted to try to hit our web browser, not going to let us do that either. And let's say that we wanted to try to SSH. It's definitely not going to let us do that. Okay, if we look at our configuration, you can see that we have a single Ethernet card and the address is our private subnet. So we're really not getting out anywhere through that. But we do have DNS access so that we could say, for instance, install packages on this machine. So since we have DNS access, we're going to do some simple command execution and exfiltration. So let's say that we had a worm on here or a rootkit somehow. Okay, how might we get out to our command and control server to figure out what we're going to do? So one thing that we can do is we can run dig, which is the DNS lookup for a special text record that I've created on the domain. And you can see that this comes back with this, looks like gobbledygook. But what this really is a base 64 encoded string. It doesn't look particularly troublesome or suspicious, and it's only a few bytes. So running this command is not going to, alert any sort of, intrusion detection system. But what we can do with this is decode it and you can see that string there decodes to a command for our worm or rootkit, and it's going to say to execute this at June 1st at midnight. So just through DNS, we were able to get a command through to our secure system. So very low throughput, unidirectional. We can do the same thing in the other direction though, exfiltrate data. And in order to display how to do this, I created a simple bash script. So this bash script, all it does is it just takes some input. It encodes it in base 64. It attaches it to a subdomain, and it runs dig, just like we did the other direction. So let's go ahead and run this. Okay, so let's put in a secret code. Let's do hello world. Alright, so you can see that it took hello world, it encoded it in base 64, it appended that to the front of a special subdomain, exfiltrate.dnsburglar.com, and then it ran dig in order to do the server lookup. So what did that actually do? If we go back to our accomplice name server, so first of all what we can do is take a look at our logging. And so we have a logging rule in here that just takes anything that goes to exfiltrate.dnsburglar.com and sends it to var log exfiltrate.log. And if we take a look at that, you can see that the last line is our special base 64 encoded string. And so in order to do something with that, I created a Perl script a very simple Perl script. It just uses the base 64 module. It takes our exfiltrate.log, takes the last line from that. It pulls out just the special code part, pulls that off the domain. Base 64 decodes it, and then outputs it to a website. And so what we get is, if we go to our website, www.dnsburglar.com, there it is. We have exfiltrated our secret code hello world to a public website now. So this could have been anything. Could have been a password, could have been a social security number, could have been a credit card number. We have this secure system behind the security groups, the network access control lists, the IP tables rules in the NAT firewall, and still we were able to get a piece of information out to the world through all of that. And it was very low bandwidth, something that would be very difficult to detect. So if we were trying to exfiltrate, say, a large amount of data, we could just do it slowly, randomly, and it would be very difficult to detect that. But let's say that we wanted to do a little bit more. We wanted to have a high throughput bidirectional tunnel. So we can do that too. Again, this is our target secure system here. Our only way out is through that NAT firewall. But what we do is we can run our iodine client. So, this is basically analogous to a rootkit or a worm that might have this as a payload. So this is our password that we set up on the server, and this is our tunnel domain. And so iodine does all the work for us. It has now set up a tunnel with the target domain server. We can actually look at the status of that. And so these two are now connected. And we can show that if we take a look at our if config, we now have a virtual interface that has an address of our target, of our accomplice name server in Germany. So here we are on our target secure system, behind all of that protection, with a direct tunnel out to Germany. And to show that that's open, we can actually ping that, which, remember, before, ping through our normal channels is completely disabled. But we're able to ping out to that IP address. You can see the route. So we have a route now through that interface, DNS 0. We can ping our own domain now. We can go out to our website. So there's a website. If we click on our iframe, there's our secret code. And we can actually SSH out now. So here we are now SSH'd into our accomplice name server from our target secure system. So at this point we can create a SSH tunnel back to our target secure system and essentially do anything in and out through that tunnel. We can visit any website, we can SSH out to any other system. Essentially we've shown that we've defeated all security on our target secure system through our network access control lists, through our NAT firewall, through our security groups. The DNS tunnel has allowed us to basically defeat all security.